We're now going to learn about another potential flow element that is commonly used that's actually the combination of two other potential flow elements. So, and this is called a line doublet or doublet flow, or I've also heard it referred to as a dipole. So consider a source, a point source or a line source, and then a little distance away we have a sink that is equal and opposite in magnitude, and we're going to put these a distance between each other of 2 times d. Okay, and we're going to say that the strength of these is inversely proportional to the distance between them. So we're going to call it, our proportionality factor is kappa over 2d. So so as they get closer to each other, the strength goes down. Okay, so we can look at in the limit as d approaches 0, what this system looks like. And so let's just draw our 2 dots here. They're going to be really close together, and this flow field is going to look like something like this. Okay, so it'll still be flowing out of the left one into the right one, but as it comes close together, it starts to create a shape that looks something like this. And we have a direction here. I'm just going to put an arrow out. That's the direction of this doublet. We call this the doublet when we bring these two infinitesimally close together. And that direction, in the way that I've drawn it here, is pointing to the left, and it has a strength. This doublet has a strength of kappa. Okay, so the potential flow, or the velocity potential for this object can be written as kappa over 2 pi times the cosine of theta divided by r. And if we take the gradient of that to get the velocity vector, we get minus kappa over 2 pi cosine of theta over r squared in the r hat direction, minus kappa over 2 pi sine theta over r squared in the theta hat direction, and nothing again in the z hat direction. Okay, now we can also generalize this. We could actually put this doublet on an angle. So let's just draw a doublet on an angle here. Something like that. And so there's our direction there of kappa. And we'll put that at an angle of alpha there to the horizontal. Then we can generalize this equation here, which just assumed that kappa was lying on the x-axis, but we could generalize that if we have a rotated doublet, and that equation, the velocity potential, would be kappa over 2 pi times cosine of theta minus alpha over r, and then the velocity vector is minus kappa over 2 pi cosine of theta minus alpha over r squared, and that's in the r hat direction, and then minus kappa over 2 pi sine of theta minus alpha over r squared, and that's in the theta hat direction, and again nothing in the z hat direction. So basically we just replaced theta in the previous equation with theta minus alpha, and now we can rotate that doublet by alpha. So this is a potential flow element that we're going to use, or is commonly used as we're developing potential flow, or estimating the potential flow around these objects, these 2D objects that we'll be studying. And again, they can be called a line doublet or doublet flow or a dipole. But yeah, this is the development of that. It's actually the summation of a source and a sink, a positive source and a negative source, as they come infinitely close together.